Today I'll be presenting Suspension AI, a system designed to monitor vehicle suspension health in real time and alert drivers before problems become dangerous. So let's start with the problem. Most everyday vehicles have absolutely no built-in system to tell you how your suspension is doing. You only find out something's wrong when you feel excessive bouncing, your handling gets unstable, or your braking distance increases. By that point, the damage has already been done. This leads to two real consequences: safety risks on the road and expensive repair bills that could have been avoided. The question I wanted to answer was, can AI detect suspension problems early before the driver even notices them? And the answer is yes. The proposed solution is a three-part system. First, an accelerometer sensor mounted on the vehicle's chassis collects vibration data. Second, an AI-trained model analyzes that data and detects abnormal patterns. Thirdly, a mobile app receives the result and pushes an alert directly to the driver's phone. It's practical, low cost, and designed to work on any vehicle, not just expensive modern cars. For the data, I used a real multivariate vibration dataset containing 35 elements and over 46,000 rows of sensor readings. The columns include accelerometer RMS values, current, temperature, and pressure, all of which are relevant to mechanical fault detection. Crucially, the dataset includes labeled anomalies, where 0 means normal operation and 1 means a fault is occurring. Before feeding this into the model, I built a pre-processing pipeline in Python. This involved selecting the relevant columns, applying a low-pass filter to remove noise, and extracting features using rolling windows. Things like RMS acceleration, mean, standard deviation, and peak amplitude across each time window. I trained and compared two models. The first is a random forest classifier, a supervised model that learns from the labeled data. It was trained on 80% of the feature dataset and tested on the remaining 20%. The second is an isolation forest, an unsupervised model that only learns what normal looks like and then flags anything that deviates from it. The reason I included both is because in a real-world scenario, you won't always be able to have labeled suspension fault data for every vehicle. The isolation forest represents what you'd use in actual deployment. It just learns the car's normal baseline and detects deviations. The random forest, with its labeled trained data, is used here to validate that the approach works and the features are meaningful. And the results speak for themselves. The random forest achieved 99% accuracy with an F1 score of 0.983, meaning it correctly identified nearly every anomaly in the test set with a few false alarms. You can see this in the confusion matrix here, where misclassifications are minimal. The ROC curve shows an AUC very close to 1, confirming the model is an excellent classifier. The importance chart tells us which signals matter most. Accelerometer RMS features dominate, which makes physical sense since suspension faults directly affect vibration. And finally, the anomaly detection over time chart shows the model correctly flagging fault periods in the live signal. To bring this to life for the end user, I designed and built a mobile app prototype called SuspensionAI. The app walks the driver through creating an account, registering their vehicle, and connecting to the ESP32 sensor via Bluetooth. Once connected, the app displays a live health that updates in real time based on the sensor data. When the AI detects an anomaly across multiple consecutive windows, the app fires a push notification, telling the driver exactly what's wrong and where. You can see the full prototype here, including the fault simulation that triggers a live alert. One of the key design goals was making this work for any vehicle, not just one specific car. Here's how that works. When you register a vehicle, you enter the make, model, and the year. The ESP32 sensor is physically mounted on that specific vehicle's chassis. On first setup, the app runs a calibration phase. It learns that specific vehicle's normal vibration pattern over a few minutes of driving. From that point on, the AI compares every new reading against that vehicle's personal baseline, so the system can adapt. Of course, deploying this on a real road introduces challenges. Speed affects vibration, so the system normalizes readings by speed range. A single pothole should not trigger an alert, so the faults are only flagged when 3 or more consecutive windows are anomalous. Passenger loads can change the baseline, so calibration is done under normal conditions. And powering the ESP32 is simple. It runs off the car's USB port or 12V adapter. To summarize, the project demonstrates that AI can detect vehicle suspension faults with 99% accuracy using real vibration data. The full pipeline from raw censored readings to mobile app alert is practical, low cost, and scalable to any vehicle. Early detection saves lives and money. Thank you for your